Okay. Next, let us compute the electric field inside the atom. And let us look at this energy equation again. We have the kinetic energy plus the potential energy. That's the minus EB. And this is minus 13 plus 13.6 electron volts. This is minus, this was twice in magnitude of that, 2 times 13.6 electron volts. And that's equal to, of course, minus 13.6 electron volts. Let's look at the potential energy. So it's roughly, let's say, minus 27 electron volts. Potential energy, which is minus 27 electron volts, that's equal to minus E and E over 4 pi epsilon 0 1 over R0. And if I multiply it by R0 and divide by R0, now, I will cancel the minus signs. So 27, let me just do it here. 27 electron volts, that's equal to E times E over 4 pi epsilon 0, 1 over R square, R0 square, times R0. If you notice, this is the, what is it? This is the proton, here is the electron at a distance R0 away. This is the electric field at the position of the electron. Electric field due to the proton at the position of the electron. So this is electron volt, namely electronic charge times 1 volt. So this is the electronic charge. So the beauty is that I can cancel these. And this is just the electric field. Let me denote it like this with double things so that it doesn't, we don't get confused with the energy. This is the electric field. Electric field. Electric field due to the proton at the site of the electron. So 27 volts divided by R0, that's equal to E, electric field. How big is that? That's 27 volts divided by R0 is 1/2 times angstrom. It is 1/2 angstrom. It's here. So 1 angstrom is 10 to the minus 10 meters. 10 to the minus 10 meters. So it is 5.4 times 10 to the 11 volts per meter. Here, this one comes 10 to the 10. This is 54. I divide by 10, multiply by 10. So this became. So this is the electric field at the site of the electron. Units being volts per meter in the MKS units. Now the question is, well, obviously this is a big electric field, but how big is it really with respect to our daily lives, daily electric fields we encounter? So one, for example, let us take a parallel plate capacitor. These are metal plates charged to voltage. So delta V. Let's take a 12 volt battery. A voltage difference of 12 volts between the plates, parallel plate capacitor. And let's take this D as, let's take it as 2 millimeters or 2 times 10 to, in MKS, 10 to the minus 3 meters. So the electric field, electric field times D, that's equal to voltage. So E is 12 volts divided by 2 millimeters, 2 times 10 to the minus 3 meters. That's equal to 6 times 10 to the 3 volts per meter. So, all right. These are the electric fields we encounter in daily lives. We have capacitors and things like this. These are the, so 10 to the 3 volts is 1000 volts or kilovolts. So it is 6 kilovolts per meter. So roughly speaking, we have, like, let's say, of the order of 10 kilovolts per meter. And this we can just say, okay, this is something like 10 to the 12 volts per meter is an order of magnitude. And if you divide E atom over E daily reasonable electric fields, 4, that's 12, number is 10 to the 8. So the atomic electric field is enormous, 100 million times stronger than what you would get an electric field between the capacitors. So it's a terrific electric field. All right. So let me just write here. Rn is n square R0, R0 being 1/2 angstroms. R0 equals 1/2 angstrom. Epsilon n is equal to epsilon 1 over n square, or let me write like this. En is minus 13.6 electron volts divided by n square, and the atomic field is like 5.4 times 10 to the 11 volts per meter. Tremendous electric field. Okay, we now consider the magnetic field. I'm erasing this. To estimate the magnetic field in the hydrogen atom, let us again take a very simple model. Consider, for example, a charge going around the loop. So if the current is I, so this is R, this is dl, direction of the current, and the current is, let's say, I. This is R, and the Biot-Savart law gives dB is equal to mu 0. Again, we are in the MKS units. Mu 0 over 4 pi I dl cross R over R square. R looks from the current element dl toward the center. I'm computing the magnetic field at the center of the loop. So this is a current loop. I'm looking at the magnetic field at the center of the loop. So if this is the electronic current, I'm looking at the magnetic field at the site of the proton. R is a unit vector. So dl cross R. dl is this way, R is looking into the, dl cross R is along the z direction. So it is simply R d theta z. So dB is along the z direction. So it is, this R comes from dl. The magnitude of this thing is 1. Therefore, it is mu 0 I over 4 pi R over R square. And the integral of d theta is 2 pi. So the result is mu 0 I over 2r. That's the B. So if you have a current loop like that, at the center, circular loop, at the center, this is the B, mu 0 I over 2r. Now what is the electronic current then? Current is delta Q delta T. And what is it for the electronic current? It is its charge divided by the period, or E times F. And F is V over 2 pi R. So B will be equal to mu 0 I, which is E V over 2 pi R times 2R. R's we know. Mu 0 is a well-known constant. So what is the velocity of the electron? So we have to estimate the velocity of the electron. The attractive Coulomb force is responsible for the circular motion. So it is mv square over r. So this is the magnitude of the force is E square over 4 pi epsilon 0 1 over r square is equal to mv square over r. And this cancels. V square is then E square over 4 pi epsilon 0 over mr. Let me divide by c square. V square over c square is equal to E square over 4 pi epsilon 0 over mc square times r. But if you notice, this part is just the potential energy in the energy. Remember, energy is kinetic energy plus potential energy, and the magnitude of the potential energy was E square over 4 pi epsilon 0 r, I mean r0, and this was twice that, twice the kinetic energy. Therefore, this is 27 electron volts. This is 2 times the 13.6, and this is 1/2 10 to the 6 electron volt. So this is 54 divided by 10 to the 6. And this is V over C square. So can we write this as a square of something? Roughly speaking, this is like 7.5. This is 10 to the square. Therefore, V over C is like, let's take this, this is 10 cubed. Right? Square is 6. So this is like 10 divided by 10 cubed. So this is like 1 over 100. So the velocity of the electron in the lowest energy state is about 1/100th of the speed of light. The question is this, well, it is very much faster than the rocket speed and all that. The thing is that, is our electron relativistic? Is 1 over 100 indicating relativity? I'm erasing these parts. All right. Let this stay, we oversee. Is this relativistic? Well, in relativity, we have this famous gamma factor, which is 1 over root 1 minus v over c square. So if v over c is small, we can expand it. We can write this 1 plus minus v over c square minus 1 half. So 1 plus x to the p opens like 1 plus p times x. So we can estimate 1 minus 1 half times this makes it plus 1 over v over c square times 1 half. So it is 1 plus 1 over, this is 100, so it is 1 over 20,000. So the correction to gamma is simply like 1 over 20,000. So this we take roughly as 1. Okay. Now you can estimate, for example, Large Hadron Collider at CERN. They push gamma for protons, which are 2,000 times heavier than the electron, to several thousand. Okay. Gamma at CERN is several thousand. Let me say of order 10,000. It's a terrific machine. So, all right, I'm erasing it. So it is non-relativistic. Of course, if we increase our, if you look with very sensitive equipment, measurements, of course you will observe relativistic effects. But we are just thumb rule estimations. So it is non-relativistic for our purposes. So don't worry about relativity. All right. So let's write B again. B is mu 0 I, which is E times F over 2R. I'm using R0 basically. And equals mu 0 over 2R0 E. For F, I will use V over 2 pi R0 again. Now, I will multiply by epsilon 0 and divide by epsilon 0. And I will multiply by 2 pi. No, I will just leave it like that. All right, that's equal to mu 0 epsilon 0 in the MKS units is 1 over c square. All right, this is B. Now I'm collecting the terms. All right, first let's put instead of these 1 over c square. So I have E over 4 pi epsilon 0. So this is 4 pi, this is epsilon 0. Then I have 1 over r0 square, 1 over r0 square. Mu 0 epsilon 0 is 1 over c square, so it is V over c square. I will write it like this, V over c times 1 over c. If you notice, this is just the electric field. Okay. Or another way of writing this formula is CB is equal to E times V over c. Now, V over c is dimensionless. In the MKS units, B does not have the same dimension as E. But CB has the same dimension as E. CB is in volts per meter, because electric field is in volts per meter. In Gaussian system, the magnetic field is in Gauss, and it has the same dimension as electric field. That's why physicists like Gaussian systems because E and B have the same dimension, and okay, it looks better. But in the MKS system, C and B do not have the same dimension, and in a sense, B is less than E by a factor of V over C, which is 100. Now let us look at the numerics of it. I'm erasing. B is equal to E is 5.4 times 10 to the 11 volts per meter times V over C, that's 1 over 100, and then 1 over C, that's 1 over 3 times 10 to the 8 meters per second. Everybody is in MKS, so that it will come out to be the B in Teslas. So this is 10 to the 10, gives me 5.4 divided by 3 is 1.8, so it is 1.8 times 10 Tesla, which is 18 Teslas. Okay. So what is this? The magnetic field at the site of the proton due to the electronic current is 18 Teslas. Okay, well, let's compare it to a macroscopic current loop and compare. Before then, however, let me just make before that comparison, we used F with V over 2 pi over R, which is 1 over T. Let us estimate how many times does the electron go about the proton. So one quick way of estimating is 1 over, I multiply E, T and E. This is like delta T, this is like delta E. Product is like H bar. I multiply by C, and so this is like 13.6 electron volts. This is H bar C is 2000 electron volt and angstrom, and C is 3 times 10 to the 8 meters per second, and 1 meter is 10 to the 10 angstroms. So electron volts cancel, angstroms cancel. So it is like 3 times 13.6 divided by 2. This is like 10. So it's like 10 to the 19. So we made the multiplication. This is 10 to the 18 divided by 10 to the cubed. This is 15. This is, let's say roughly, this is just like 1. This is like 10. This is like 10 to the 19, subtract. This is 10 to the 16 revolutions per second. So tremendous. Imagine 10 to the 16 revolutions per second. You can also estimate, of course, F from here. F is equal to V over 2 pi R and V over C, C over 2 pi R. This is like 1 over 100. And you plug in the numbers. this will turn out to be again of order 10 to the 16. So 10 to the 16 revolutions per second. We say for a short time the blink of the eye, and in the blink of the eye the electron is going about the proton 10 to the 16 times, an incredible number of times. Okay, now coming back to magnetic fields on daily life, I'm erasing this. So let's take a current loop, for example. Let I to be 10 amperes. And let's take an easy radius. Let's say 10 pi centimeters. So B will be, B is equal to mu 0. That's 4 pi 10 to the 7. Times 10 amperes. It has some units I will not put in the MKS system. Divide by 2R. 2 times R is 10 pi times 10 to the minus 2 meters. This is amperes. Okay. The result will be in Tesla. That's why I took pi, so that I can cancel this. Okay. This is 8. Sorry, this is 10 to the minus 7. 4 divided by 2. 10 times 10 to the minus 6. Minus 5. So say 20 times, I multiply 10 divided by 10, 10 to the minus 6 Teslas. So let's compare with the atomic field, 18 Teslas. Actually, if you put in the numbers, it will come out to be less than 18, something like 12 or 13 or something like this. It will be a bit lower. But it's close to numbers here. So B atom, B daily. So ordinary magnetic fields are in micro. This is 1 micro Tesla, millionth. So B atom over B daily magnetic field is something 20 cancels 18. So it is 10 to the 6. So it is atomic magnetic field is 1 million times stronger than an ordinary magnetic field you will encounter in your daily life. So if I summarize, E atomic is like 10 to the 8 times E daily. By daily, I mean in your daily life. This is the these are the electric fields, not energy. And B atomic, by atomic I mean hydrogen in ground state. Okay, is like 10 to the 6 times B daily. So these are enormous fields. And, well, I think we now have an idea about the hydrogen atom, namely that its size of the order of angstrom and its energy, binding energies En is minus 13.6 divided by n square, and Rn is n squared times R0, which is 1/2 angstrom. And it has a very strong electric field and magnetic field inside the atom. All right. This is the impression we get about the hydrogen atom before we begin to solve it, solve the Schrödinger equation, before we attack the problem with full quantum mechanical approach. Thank you.